All right, in this section I have quite a bit to talk about, and it is dealing with concavity and the second derivative. I'm first going to define being concave up as somewhere on the interval where f prime of x is increasing. So if I extend this out just a little bit more, f prime of x would be a negative number, and then it's less negative, then it's 0, then it's more positive, more positive. So you can see how f prime of x is increasing. So concave up looks like this. If the derivative of the function is decreasing, so here it's positive, then it's 0, and then it starts becoming negative and more negative. So f prime of x is decreasing on that interval, then I know it's concave down. And this is what concave down looks like. Going a little bit further into this, I want to just show you another picture. Interval A to C, the open interval A to C is concave down. How you can remember that is it won't hold water. From C to E, it's concave up, and it will hold water. The point of inflection, so where it changes concavity. Let's write that in there. This is where it changes concavity. Points of inflection. So we have critical numbers that we look for when we're increasing and decreasing, and now we have points of inflections. Points where things could change. Could, this is a key word, from concave down to concave up or concave up to concave down. How we're going to determine whether it's concave up or concave down is by looking at the second derivative. If the second derivative is positive throughout an interval, then we're going to say it's concave up. If the second derivative is negative throughout an interval, then we're going to say it's concave down. So this one was negative, this one was positive. So if it's positive, it's concave up. If it's negative, it's concave down. And the other thing we're going to take note of is that f double prime, if it's equal to c or if it's undefined, then there's a possible point of inflection. Possible. It doesn't have to change concavity, but sometimes it does. What we're going to do is we're going to practice drawing a few of these things. We're going to draw a decreasing function that is concave down. So what I'm going to do is kind of just sketch here. Decreasing would look like this. Now I want it to be concave down, so that's going to not hold water. So I'll put a dot right here, and then I'm going to make it stay decreasing, but notice how it's concave down. This wouldn't hold water. If the water hit it, it'd run off. A falling function that's concave up. So a falling function would look like this, okay, but if it's concave up, it's going to hold some water. Okay, so it's falling. This is concave up. It wouldn't hold a lot of water, but it would hold some water. An increasing function that is concave down. So increasing means it's going to be going up like this. Concave down, it won't hold any water, so it's got to be curved like this. Going on a few more of these. An increasing function that is concave up. So we've got increasing again, and we want it to be concave up. So we will have it holding water. The number 5 says, let's sketch something that is, this means increasing, right? Greater than 0. The first derivative is greater than 0 everywhere. So it's increasing everywhere, but the second derivative, remember, applies to concavity, and it's concave down everywhere. So we want it to be increasing everywhere, but concave down everywhere. So we could just create a function that looks like this. It's increasing, but it's concave down everywhere. The last one of these sketching says that we're going to create a graph that is increasing with a point of inflection at 0, 0. So I'm going to go ahead and just start to draw this graph. I've got 0, 0 as a point of inflection, meaning it's either changing from concave up to concave down or vice versa. Right here it tells me this is concave down because it's less than 0, and this means concave up because it's greater than 0. So when it's less than 0, I want it to be concave down, so I'll make it look like that. That would be concave down. And then at 0, it changes and it becomes concave up. Okay, we're going to do lots of examples where we go ahead and find these places of concavity. Remember that concavity occurs at the second derivative, so that's what I'm going to start out by doing. I'm going to take the first derivative, and then I'll take the second derivative, and the second derivative negative 6x plus 6. We're looking at where the second derivative has possible points of inflection, so where it does not exist. There are no values where it does not exist or where it is equal to 0. Solving for x gives me x is 1. We're testing these possible points of inflection for the second derivative. We want to know what's going on with the second derivative. If the second derivative is greater than 0, if it's positive, then we know it's concave up. If the second derivative is negative, meaning less than 0, then we know it's concave down. So let's test this interval. Let's put 2 in. Let's say we have negative 6 times 2 plus 6. That gives me a negative value. And then right here, when I plug in 0, I have negative 6 times 0 plus 6, which gives me a positive. So that means my interval of concave up is from negative infinity to 1. So it is concave up here because the second derivative is positive. It is concave down from 1 to infinity because my second derivative is negative. This next example, we are going to find the second derivative. I noticed that this will be much easier to take the derivative of. Rather than using a quotient rule or chain rule, let's just change this into 2 cosecant x. Take note of the interval we're looking at. We're only going from negative pi to pi. So we're going to go ahead and find the first derivative. That gives me 1 plus 2. The derivative of cosecant is negative cosecant x, cotangent x. And then we'll go ahead and take the second derivative. Second derivative just ends up being the 1 is 0, so we have a product rule right here. I'll underline my first and second part. So I'll say first times the derivative of second. The derivative of cotangent is negative cosecant squared plus cosecant x times the derivative of the first part there. So it would be negative 2 cosecant, back up, the derivative of cosecant is negative. So I'll have negative cosecant x cotangent x. Well, this will simplify to give me a positive 2 cosecant cubed, because I've got 3 cosecants. A negative times negative 2 is a positive 2, plus I have negative 2, and then inside of here, actually that changes to positive, because then negative 1 times negative 2 is a positive 2. I have a positive 2, and I have 1 cosecant x, and I have 2 cotangent x's. This will simplify further. What I can do is factor out a 2 cosecant x. That leaves me with cosecant squared x plus cotangent squared x. This actually equals 1. This is one I picked this problem is because it's a little bit more difficult. That equals 1. And then I'm going to go ahead and write my second derivative as 2 over sine x. Now remember, our goal is to find the possible points of concavity. So I want to look at where it is 0, which this second derivative will never equal 0, or where it does not exist. So where it does not exist is when the sine of x is equal to 0. Well, the sine of x equals 0 when x is 0 only. So it is, I can write undefined at x equals 0. That's my only possible point of inflection. But remember, I'm only going from negative pi to pi, so I only need to test these particular intervals and see what's going on with the second derivative. Remember, everything entails a second derivative. So when I plug in pi over 2 in for here, at pi over 2, I end up with a positive value. And when I plug in a negative pi over 2, I end up with a negative value. So it is concave down from negative pi to pi, or negative pi to 0, and concave up from 0 to pi. So it's concave down here and concave up. The next thing we're going to start to talk about is the second derivative test. And the second derivative test is a quick way to test whether it's a max or a min. So if you find your first derivative and you see that your second derivative is negative, then you know it has a local max. If you have your first derivative, your critical number, and you test that critical number into your second derivative and you find out it's positive, then it has a local min. It's easier to kind of see this in a problem. So what we're going to do is take and find the second derivative. So let's see here. The first derivative ends up being negative 2 x minus 5, and I'm going to then, and that's it, distribute this, so I get negative 2x plus 10. Well, my second derivative just happens to be just plain old negative 2. This problem makes life really easy because I can then test what my critical number was. I need to go back up here and find my critical number to find out where there is relative extrema. So where is my first derivative equal to 0? Well, it's simply just at x equals 5. You're going to test that in here. Well, there's nowhere to even plug that into. It just means that it's concave down everywhere. It's concave down everywhere. So I need to say that at 5, it's concave down. So this would happen to be a max by the second derivative test. The next thing we're going to look at is this problem. What I'm going to do is I'm going to find the first derivative, and I will get my critical numbers. So I end up finding out it to be critical numbers when this is factored. This is x minus 3 times x minus 3. So my only critical number is at x equals 3. I want to know if it's a max or a min. So I'm going to use the second derivative to test that. I could test it with intervals too, just like we did in section 3.3. But I'm going to use my second derivative test. It's a little bit faster because my second derivative is very easy to find. When I plug in 3 into my second derivative, I end up finding out, well, I get 0. So it's neither concave up or concave down, and I can't use my second derivative test. So while I thought this was going to be easier, it ends up being a little bit more work. So the second derivative test does not apply because I didn't get a positive or negative value. If I would have, I could have just been done. But I need to use my first derivative test, which says I'm going to plug in 2 for this derivative here, and I'll find out that I end up getting positive on both sides when I test those. So what this means is that it's increasing everywhere and it has no relative extrema. Please ask me to do another type of this in class.